Welcome back. So, we looked at in the last class we looked at how the different chemical shifts arise due to what are the different effects which factors which influence these values. We looked at inductive effect and we looked at mesomeric effect. So, let us continue with the mesomeric effect now and see some more examples how in the aromatic systems especially. So, here you can see the example of aniline. Alanine is a well known molecule and this is the structure. So, if you look at this functional group NH2, it is an electron donating group. So, it is an electron donating group. So, what happens is it donates a lone pair of electrons towards this ring, and because of this situation you end up with a little higher electron density around this ortho hydrogen. So, this ortho hydrogen accumulates electron density which in turn is transferred to this hydrogen. So, this hydrogen is also having a higher electron density compared to the case where there was no aniline NH2 groups amine group. So, you can see because of this higher electron density, this hydrogen atom now appears de-shielded or sorry shielded. It comes at a higher, that is lower chemical shift value, it is shielded. So, this you can see this value here, it is around 6.5 ppm compared to the other hydrogen which is meta hydrogen where it is de-shielded. So, this is typically the value you will see in the benzene ring, in aromatic benzene ring. So, that is a normal 7 ppm, but with respect to that value this hydrogen has got upfield shifted because of this electronegative, this is because of this electron donation and because of the higher density of the electrons accumulated at the ortho position. The same thing can happen in para position. So, if you continue this resonance delocalization of this electron, you can see even in the para position you can this carbon may have a higher electron density around it, which in return transfers electron density to this hydrogen. So, overall this system has a very high electron density around this hydrogen, and therefore, again remember if you have higher electron density it is shielding and lower electron density is de-shielding. So, the higher electron density causes a shielding of this hydrogen and it comes at a lower ppm value compared to the hydrogen in the meta position. So, this is how mesomeric effects influences the chemical shifts. We can see you can get more varieties of more examples in the different books which we looked at in the very first class. So, I would recommend to go through those examples. Typically this is how one can explain based on the electron withdrawing group or the electron donating groups, donating nature of the functional groups. So, we look at another effect because of which electrochemical shifts change, and that is called as a ring current effect. So, this is very typically observed in only the aromatic rings, and this is called ring current effect. So, in aromatic systems what happens is the ring, there is a delocalization of this electron around the in the aromatic ring. So, this is schematically shown here. Now, again remember any moment of electron, that is a moment of charge, generates a magnetic field, and therefore, because of the circulating pi electrons there is a magnetic field around this particular ring, and that the magnetic field lines are shown here by this grey color arrows. So, you can see the magnetic field is going into the plane of the ring and then comes out and then it is. So, if you now look at an hydrogen atom, let us say which is located at this position, in that particular hydrogen atom this magnetic field lines are coming into the ring and they are in the opposite to this particular magnetic field which is shown in the yellow color. So, what is happening is that this the electron because of the circulating electron density, the magnetic field around this hydrogen is being shielded, means being opposite compared to what is in the main magnetic field. Therefore, this hydrogen is which if hydrogen is located here becomes shielded. Shielded means it comes at an upfield position, whereas if you look at an hydrogen atom which is located in the plane of the ring, in the plane. So, if you look at this case here, this electron, this magnetic field is coming in the vertical direction and it is in the same direction as this yellow color the field direction of the main magnetic field. So, you see here also this hydrogen, this electron, this cloud and this magnetic field is actually supporting, or is it in the same direction as the main magnetic field, and therefore, this magnetic field and this magnetic field they add up together and that basically increases the magnetic field. In other words, it results in de-shielding of this hydrogen. It is not shielded, the shielding means opposing the main magnetic field, de-shielding means supporting the main magnetic field. So, you can see here it is a support of the main magnetic field and therefore, this hydrogen appears de-shielded. and that is the reason why in a NMR spectrum you will always see the aromatic ring protons, means the ones which attached to the ring, always coming at around 7 to 7.5 ppm, because they are in the plane of the ring. But if the structure of the molecule is such that if there is any hydrogen coming on the top of the ring, will appear de-shield, it will be appear shielded. So, we will see examples of this type of systems in the next slide. Here you can see there is an aromatic system. So, here what happens is this is an aromatic ring, and you can see that these hydrogens which are away from the ring, which are in the on the top of the ring. So, these are two hydrogen atoms which are on the top of the ring. Because of this ring current effect, they are highly shielded. When you say highly shielded, it comes at a low ppm value, and that is 0.8 ppm. But those which are towards the ring, the plane of the ring. So, you can see these hydrogens are more towards the plane of the ring, and if you remember the flux, that electron, the circulating pi electron, this side the main magnetic field and the field because of the ring, they add up together, and therefore, they become de-shielded. So, de-shielded means they come at a lower ppm, higher ppm value, and that higher ppm value is because of that it comes at 2.6 ppm compared to 0.8 ppm, which is at the top of the ring. Similarly, if you look at this particular system here, if you wish look at this plane, you can see this CH3 is right on top of this aromatic ring plane. So, this is a planar structure of aromatic ring, 4 electroaromatic rings fused together, and this hydrogen is located right on the top of the ring, and therefore, it becomes highly shielded, and in fact, it comes at a very low value of minus 4.25 ppm, it is a negative ppm. Negative basically means it comes even more upfield compared to TMS, which is our reference, that is our 0 ppm is reference, and it comes on the negative side of the TMS. So, that can happen because this hydrogen is right on top of the ring, and that is a shielding effect of because of the ring current, and any hydrogen which is located on the plane of the ring will not experience that shielding effect, and it will typically come at the ppm value of benzene ring, which is 7 ppm. So, aromatic ring current effects are very important for understanding the structure of molecules. In fact, in biomolecules, if you consider proteins, proteins have aromatic amino acids known such as tyrosine, phenylalanine, histidine, and tryptophan, and so on. So, whenever you have this aromatic rings, any hydrogen atom which comes close to this ring get very much highly influenced by this ring current effect, and ring current affected chemical shifts in fact are very important in determining the structures of lots of molecules. So, we will look at that aspect in a later time. Let us continue with the next effect of chemical shift by that is called steric effect. So, steric effect as we learn in chemistry is basically the crowding effect. That means if you have two bulky groups around the molecules, they cause, because of the steric effect is the influence on the structure of the molecule. So, for example, you can see here that the methyl group is de-shielded by one bond. So, if there is a carbon bond, a single bond, and these 3 hydrogens are located on one side, and because of this group, this is carbon atom sitting here, this particular hydrogen is influenced, and that gets de-shielded. When you say de-shielded, it means it comes at a higher ppm value. So, suppose there was no carbon here. If there was no carbon here, you would have another hydrogen which is methane group. A methane, as we saw in the last class, it comes at around 0.23 ppm, but because of this additional carbon atom, this will now affect this proton. And suppose let us say you have another methyl, which is if you have 2 methyl groups, that is an ethane molecule, and in ethane we saw that the hydrogen atom has a chemical shift value of 0.8 ppm, 0.86 ppm. So, you see it has moved from 0.23 in methane to 0.8 in ethane group. So, this is the effect of the steric group because of the additional carbon atom. Similarly, if I keep adding more and more carbon atoms, when you have a secondary carbon, tertiary carbon, you can see that the hydrogen atom gets more and more de-shielded. So, in this particular example, these 2 hydrogen atoms are now experiencing the steric effect of 2 more carbon atoms compared to 1 here, and therefore, these 2 will be more de-shielded because compared to these hydrogen atoms. Similarly, if you have a tertiary carbon, you can see the methane group, you will have further de-shielding because of 3 carbon atoms attached to this carbon compared to 2 and 1 here. So, that is how the shielding effect is influenced, the shielding factor is influenced by the presence of multiple carbon atoms around this hydrogen. So, one of the important effects is called hydrogen bonds, and we have this is very important because many of the organic molecules or biomolecules have hydrogen bonds in their structures. So, all of us know what is an hydrogen bond. The hydrogen bond basically is an attraction. So, basically there is a donor atom which is electronegative and there is an acceptor electronegative. The both of them compete, or they both of them one of them is bonded to hydrogen, the other one is electrostatically attracted to this hydrogen, and therefore it forms a very weak bond between this hydrogen and there is oxygen here, and because of that what happens is there is an additional. So, this is the covalent bond here for example, which is already attached to this oxygen, but there is a weak dotted line hydrogen bond between this hydrogen and this oxygen, and what happens is because of this additional extra bond, the electron density around this hydrogen is reduced, because now there are two electronegative groups which are competing for the electron density around this hydrogen. So, this hydrogen experiences a low electron density, which means it gets de-shielded. So, hydrogen bonds or hydrogen atoms are involved in hydrogen bonds are typically de-shielded, and you can see that actually there is a large variation because of hydrogen bonding. The alcohols OH groups, because of hydrogen bonding, they come at as downfield, de-shielding means downfield, and they come at as much downfield shift as 5 ppm. So, this is the effect of hydrogen bonds, and it is very important to know that effect of hydrogen bond on de-shielding and shielding effects, because again it is based on the structure of the molecule, and lot of information we get knowing the chemical shift based on hydrogen bonds. So, this is another example here. So, one of the thing what typically we do, we will look at it again in a later point of time, but to tell you in a very quickly is that one of the ways to find hydrogen bond is present in a molecule or not is to simply record the spectrum of the molecule at different temperatures. So, as you go to higher temperatures, what happens is the hydrogen bond breaks, because hydrogen bond is not a very strong like covalent bond, it is a weak in energy. So, as you increase the temperature, it has a tendency to break, and the moment the hydrogen bond breaks, the OH chemical shift, the hydrogen atom which is involved in hydrogen bond suddenly experiences an upfield shift, meaning it basically goes towards lower ppm value, it goes toward the right side, and that basically indicates there is no hydrogen bond. And if you go to lower temperature, this hydrogen bond becomes more strong and it goes to lower downfield shifted if there is a hydrogen bond. So, of course, these are shown for different molecules, but the idea is that this molecule, if a peak shifts because of the temperature very strongly, if it shifts, it is one of the indicator that that particular hydrogen may be involved in a hydrogen bond, and therefore temperature dependent effect of on chemical shift is used as an indicator of the presence or absence of a hydrogen bond. So, this is what is shown here in carboxylic acid. So, the carboxylic acids have very strong hydrogen bonds, they form kind of dimers, that is well known, and that is why they have a very downfield shifted. You can see, as I mentioned in the last class, the hydroxyl, the OH, the H atom of the carboxylate group, they come at very downfield shift around 10 to 12 ppm, and it is very easy to recognize them when you see them in an NMR spectrum, and that it is coming from carboxylic acids. You can also have intramolecular hydrogen bond such as in salicylate, here methyl salicylate, or you can have it in intermolecular hydrogen bond as shown here. So, even in the case of intramolecular hydrogen bond, the chemical shift of this hydrogen is very much de-shielded, means it comes at a very high ppm value, and that is typically, in this particular case it comes at around 14 ppm, which is very high downfield shifted proton compared to any other proton. So, that is one of the indicators of hydrogen bond, but of course, we cannot say directly whether it is intramolecular hydrogen bond or it is intermolecular hydrogen bond, but that for that one has to do some more experiments which we will see in the later point. So, now we will come to a very different concept. So, we have seen how the chemical shifts are influenced by various factors. Another important point or topic or concept in NMR is called chemical and magnetic equivalence. So, this is very important to understand. Let us see what this means. So, what happens is many times two hydrogen atoms will have the same chemical shift. So, why does it have the same chemical shift? The reason is that they have identical chemical environment around them. So, this is one of the reasons two hydrogens can have same chemical shift value. Remember, chemical environment means electron density. So, if two hydrogen atoms have such an electron density that the shielding factors are same for both of them, then the chemical shift also will be same for both of them. But that is not chemical equivalence. Chemical equivalence means this is one of the conditions it has to satisfy, that means two hydrogens are same. At the same time, the two hydrogens are interconvertible. So, this is a very important point which has to be borne in mind, is that the two nuclei, that is two hydrogens which we are looking at, they are interconvertible in their positions by some kind of a symmetry operation. So, we will look at this more in detail, but this is let us look at an example here. The example is shown here on this right here. For example, thus let us say these two hydrogens, let us look at these two, or we can look at all the three hydrogens here. So, what I can do is I can convert this hydrogen into this position by simply a rotation. This is the angle between them is 120 degrees. So, by simple rotation I can change this to another this hydrogen, or I can take this hydrogen to this side by another rotation. So, by simple rotation I am able to interconvert these three hydrogens. Not only that, they are in the same chemical environment because they are all equidistant. So, when they rotate they have the same roughly average positions with respect to these three chlorine atoms. So, because of that, these three hydrogen atoms are now chemically equivalent, meaning they have the same chemical shift, same chemical environment, and they are interconvertible with respect to each other. So, one should distinguish here between two things. One is that two hydrogen atoms can accidentally by chance have the same chemical shift value. That does not mean they are chemically equivalent. When you say they are two hydrogen atoms are chemically equivalent, it means they have to satisfy both of these conditions, and that is why this word "and" comes into picture, that they have to not only have the same chemical environment, at the same time they should be interconvertible in their positions by some kind of a symmetry operation such as rotation, rotation, or a rotation around an axis, or rotation around a bond, and so on. Only when both of these conditions are satisfied, we consider that the two hydrogen atoms are chemically equivalent. If only the first condition is satisfied, if only that the chemical environment accidentally is same, then they are called chemical shift degeneracy. That means they are degenerate. The two hydrogen atoms have accidentally the same chemical shift value and they are degenerate or they are overlapped, but they are not chemically equivalent. So, we can look at some more examples of chemical equivalence here. So, this is one example. The second example is inversion around the center of symmetry. So, for example, look at this molecule here. If I take an inversion, if I can invert this to this side, this hydrogen will come here, this hydrogen will go here, and they are come back, they are chemical, they are basically positionally they are come back to their positions, in the sense they are interconvertible, they are interconverted into each other's position, but there is no difference in the structure of the molecule because of this conversion, and the molecule looks the same, and therefore, these two hydrogens are interconvertible. At the same time, they have the same chemical environment. This hydrogen has a chlorine next to it and a chlorine this side. Similarly, this hydrogen has the same one chlorine next to it and this side. So, you see the chemical environment around these two hydrogens are same, and at the same time they can be interconverted around each other, and therefore, these two hydrogen will have the same chemical shift value and they are considered as chemically equivalent. So, they will always be chemically equivalent. So, this is a trans hydrogen. We will look at more examples of this. Let us look at this particular structure. So, you can see there is a double bond here and there is a plane of symmetry, which means this is a mirror image of this. So, if you can imagine this plane as a mirror, it is reflecting this hydrogen around this mirror, and therefore, these two are actually mirror images. Means if I turn around the molecule by this around this axis, I can actually interconvert this. So, if I turn around by 180, these two hydrogens will get converted to interconvert to each other. So, there are both these conditions that they are interconvertible because of a symmetry operation, and at the same time they have the same chemical environment because they are at the same distance or same structurally similar to each other. Therefore, these two hydrogens are now chemically equivalent, and therefore, their chemical shift value will be same. They will not have different chemical shift value. You can look at this another example here. Again, we can see there is an axis of symmetry here, this dotted line shown here. So, you can see that I can convert this hydrogen to this hydrogen by inversion symmetry here. similar to what we did in the previous slide. So, again these two hydrogen atoms will be equivalent to each other. So, we can look at some more examples. So, this is another case where there is a methyl group here, a methyl group in this. Okay, we can look at this particular axial equatorial if they are interconvert. So, another reason a chemical equivalence can come if they rapidly interconvert between each other. So, this is what is shown here. Example, we know in a methyl group. So, let us look at a methyl group. We know that a methyl group very rapidly rotates around this bond, this particular single bond, if there is a single bond here. In fact, so much so that even in a solid form this methyl groups continues to rotate at a very fast time scale. So, this rotation is very rapid, and because of this rapid rotation around this bond, these three hydrogens experience the same chemical environment, because they cannot have a different, even if you have a functional group here, this hydrogen, this hydrogen, this hydrogen, they interconvert and they end up with the same chemical averaged chemical environment around themselves, and therefore, all the three are chemically equivalent. So, methyl groups are always chemically equivalent in NMR spectroscopy. It is very difficult to not have the methyl groups inequivalent. That is only possible if you freeze the methyl group, but even in a solid state these methyl groups are rotating very rapidly. So, therefore, they can, all these three hydrogens in a methyl are always interconvertible and always are very equivalent. So, this is basically the concept of chemical equivalence. We will look at magnetic equivalence in the next class. So, the take home here is that chemical equivalence is a very important point. Because of chemical equivalence, the chemical shift of all the hydrogens come out to be same, and it is important to know, because methyl groups, for example, always have the three CH3 atoms, the three hydrogen atoms are always chemically equivalent. The only way to break chemical equivalence is to put them in an anisotropic medium, but in a normal solution NMR spectroscopy, these three hydrogen atoms are very strongly chemically equivalent and you can never separate them. So, this is a concept of chemical equivalence. One has to basically look at symmetry operations. You have to look in the molecule and figure out if there is any way I can convert one hydrogen atom to another hydrogen by some symmetry operation. If we can do that, then basically the two hydrogen atoms become chemically equivalent. So, we looked at chemical equivalence. Now, let us look at what is called as magnetic equivalence. So, this is another concept in NMR. So, chemical equivalent basically means that the two hydrogen atoms are called as chemically equivalent if they are interconvertible to each other, as well as they are having the same chemical environment. Now, what is magnetic equivalence? Magnetic equivalence is follows. For this, we will have to use the concept of J coupling, which we will see in more detail in the later class, but one can still understand this concept based on the structure of the molecule. So, if you look at this particular structure, ethanol, this CH3 hydrogen atoms, this is a methyl group. So, therefore, it will be all chemically equivalent hydrogen atoms. Now, to establish whether these three are magnetically equivalent also, we will have to look at their interaction with other hydrogens in the molecule. So, chemical equivalence, remember, does not rely on the interaction of this hydrogen with other hydrogens. It is only based on the structure of the molecule and the symmetry operations. Whereas, in this particular magnetic equivalence concept, one has to also look at the other hydrogens in the molecule and then see how this particular one hydrogen interacts with another hydrogen. So, in the methyl group case, we have to see if they have the same J coupling, each of these hydrogens in this methyl group, whether it has the same J coupling with all other hydrogen atoms in the molecule. If yes, if they have the same coupling, then we say that these hydrogen atoms, these three hydrogen atoms, they are not only chemically equivalent, but they are also magnetically equivalent. So, this is the concept. So, if you look at now this hydrogen atom here, these two hydrogen atoms are chemically equivalent. Why? Because they have the same chemical environment around the two hydrogens and they are actually interconvertible by rotation. But are they magnetically equivalent? For that, one has to then consider their interaction with this hydrogen and this hydrogen, and it turns out that these two hydrogens have the same interaction with this hydrogen. The interaction is a J coupling interaction, and they also have the same interaction with these hydrogen atoms. Therefore, these two hydrogen atoms are both chemically equivalent and magnetically equivalent. So, we can look at more examples here and in aromatic system. So, let us see in the aromatic system here. Now, if you look at the symmetry operation, if you look at the symmetry, if you draw a axis line here in the center of the ring, you can see that these two hydrogens are interconvertible, means they can be, if I rotate the ring around this line, around this horizontal line, this hydrogen will come this side and this will go that side. Similarly, these two will interchange, and because of this interconvertibility and because they are the same chemical environment, this hydrogen and this hydrogen are located equally close or far from this oxygen and so on, they are chemically equivalent. But are they magnetically equivalent? For that you have to look at the interaction with all other hydrogen. So, now if you look at this hydrogen A, it has particular interaction with B, that is J coupling. So, that is separated by 1 bond, 2 bond and 3 bonds. But if you look at interaction of this A with this B, it is not the same, because it has now 1 bond, 2 bond, 3 bond, 4 and 5 bonds away. So, this A prime, this hydrogen is 5 bonds away from this hydrogen, therefore, its interaction with this is very weak, but the interaction of this hydrogen with this hydrogen is relatively stronger. So, now what happens is these two hydrogens, they are chemically equivalent, but their interaction with another hydrogen, you take any other hydrogen in the molecule, they are not same, because this one is more closer and this one is farther, and because of that these two hydrogens are no longer magnetically equivalent. So, similarly this hydrogen atoms and hydrogen atom and this hydrogen atom, you can consider the same way, that these two are chemically equivalent, but if you take any one hydrogen atom, let us take this one now, its interaction with any other hydrogen atom, this one is 3 bonds away. So, it has one type of one particular strength of interaction, J bond, J coupling, but the J coupling of this with this hydrogen is 5 bonds away. So, it is a different type of interaction, it is a weaker interaction. So, therefore, this hydrogen and this hydrogen are no longer chemically magnetically equivalent, and we say that they are magnetically inequivalent even though they are chemically equivalent. So, you see chemical equivalence and magnetic equivalence is a very important concept, that two hydrogen atoms can be chemically equivalent, but they need not be magnetically equivalent. But vice versa, if two hydrogen atoms are magnetically equivalent, they are normally always chemically equivalent. So, chemical equivalence does not necessarily establish magnetic equivalence. So, most of the time we will be worried about chemical equivalence, and we will not look at so much as magnetic equivalence. So, chemically, as long as they are equivalent, their chemical shift values do not change, and that is all will be the concern as far as the structure of molecule NMR interpretation is concerned, but it is very important to keep in mind this the concept of magnetic equivalence. So, we will look at the next in the next class, we will look at how chemical shifts now can be further interpreted, and we will look at some examples and then see how we can analyze the data. Thank you.